Okay, hi everyone. Is the sound good?
Yep.
Okay, good morning everyone. Thank you for joining this today's webinar, which will be on DC power systems analysis in passenger vehicles using EMTP. We are very happy and lucky today to receive Maxime Berger, who is from Bombardier Transportation. It's actually a good friend of us and a good friend of mine because we've done our master degree together at the École Polytechnique of Montreal. So I'm very happy to have him today. And I've seen his presentation and I think you guys will really like it. It's very interesting and very advanced technically. So Maxime, can you hear us? And can you speak?
Yes.
No, I don't have your sound. Can you unmute? Try again.
Hello everyone.
Okay, it's perfect. So now I will mute myself and I will give you the right to present your screen, and we're ready to go. Good for you?
Yes.
Let's go.
Okay, thank you, Henry. Hello everyone. First of all, I want to tell you all that I'm very pleased to do this webinar today because, as you probably already know, DC power system transient simulation is not as mature as ACs. And based on my experience at Bombardier Transportation, I think I might be able to give you important guidelines to do DC power system analysis using EMTP. So here's the agenda of this webinar. First of all, I will present you an overview of rail passenger DC power systems, which will give you a general idea of this whole world. Then I will explain to you the advantages of using EMTP to do our power system studies. After that, I will present you the models that have been developed and implemented in EMTP. After that, I will present you a different example of case study that can be done using these simulation models. And finally, I will go in the EMTP and I will show you a complete overcurrent protection example. So for those of you who doesn't know Bombardier, Bombardier Transportation is a world leader in rail vehicles manufacturing, maintenance, and fleet management. In my department, as systems integrators, our job is to make sure that all systems are correctly integrated together to execute their functions. At the design phase, it includes to achieve different analysis, such as those that I'm going to present to you today in this webinar. I strongly believe that such an expertise is necessary to design vehicles with optimal operational performance. So here, what we see is a simplified schematic of a DC traction power system. It is typically composed of multiple substations connected in parallel that feeds a track system. In subway systems, the positive rail is typically called the third rail, and the negative or return rails are what we call the running rails, here in black. The substation are generally made of 6 or 12 pulse diode rectifiers connected to a dedicated electric utility substation. Typical primary DC voltage level is between 600 volt and 1.5 kV. And the average rated power of the substation is between 2 to 5 megawatts. Inside the vehicle, what we see here is that we have the primary power, which is here in red. It is composed of the collector shoes, which are collecting the power from the third rail. And these collector shoe fuses are there to protect the primary power equipment. The high-speed circuit breaker, which is here, is there to protect the propulsion system, and finally we have a auxiliary fuse that is there to protect the auxiliary converter. In this webinar, I will show you detailed models of the substations, the vehicle primary power protective devices, which are mainly the collector shoe fuses and the high-speed circuit breaker, and also different auxiliary system components. So here what we see is a schematic of a vehicle DC auxiliary power system. We see that we have a 5 vehicles train. We have car A1, B2, C3, B4, and A5. What I can say is that rail passenger train DC auxiliary subsystems, which are represented here by the yellow boxes here, DC loads, are supplied by an auxiliary converter, also called the LVPS, the low voltage power supply. 37.5 volt DC systems are widely used in North America, while 110 volt DC is a common nominal voltage in Europe. NiCad batteries are also used to support important loads during emergency conditions, such as the loss of the primary power coming from this guy here, the auxiliary converter. The other components that we can find on the DC auxiliary systems are overvoltage protection device, such as TVS, MOV, filter capacitor, ground fault detection devices, and of course overcurrent protection devices such as fuses or circuit breakers that we can see here. So why we are using EMTP to do our power system studies? The first reason is that it provides high capabilities of simulating very large scale power systems with detailed models. And it is really important in our case because it allows to perform simulation on a train level with the required precision and with an acceptable simulation time. It also allows to simulate hybrid. When I'm speaking about hybrid system, I'm speaking about AC and DC power systems in the time domain. And it also allows to do different studies using the same models in each and every case. For example, we can do overcurrent protection analysis, ground fault protection analysis, overvoltage protection, battery sizing, stability, and rush current. And we can do all these power system studies using the same models. The only thing that's going to change is the time step. Another thing is that the iterative solver for nonlinearities provides absolute precision even with large time step. For example, it is important here when we are modeling, for example, the arc of the circuit breakers and the diode's VI characteristics. So now let's go through the models that have been developed in EMTP. The first model that I wanted to present you is a complete DC traction system model. So here, to simplify it, is composed of two substations, Substation A and Substation B, that are connected to the vehicle through an equivalent track and an equivalent feeder. So we have a subway vehicle here that is supplied by two substations that are connected to a DC feeder and a DC track. So we'll look at the substation and the vehicle models individually. So inside the substation, how it is modeled, we have a this model is based here. What we can see, this model is based on Société des Transports STM, Société des Transports de Montréal STM, 2.5 megawatt, 750 volt DC, 12 pulse parallel rectifier data. And what we see is that the two 6 pulses bridge are connected in parallel through an interface reactor, which is here. And each diode, what we see here, is modeled with an equivalent nonlinear VI characteristic. Inside the vehicle, we have the models of the primary power equipment. So that's what we see here. So we have first, we have the collector shoe fuses that are modeled in 2 blocks. The detection block, which is here, used to implement the fuse AC RMS time current curve, and the opening block, which is used to approximate the behavior of the fuse during its arcing time. The detection blocks, and what we see here, that the detection block sends the current flowing through the fuse and sends a signal to the arcing block once the melting energy of the fuse is reached according to its time current curve. The high-speed circuit breaker is also modeled in 2 blocks. We have the detection block, which is here the HSCB trip coil, and the second block, which is used to approximate the HSCB arc as defined by HSCB manufacturers. The detection block sends a signal here to the HSCB trip coil, and this detection block takes into account for the detection and mechanical opening delays of the circuit breaker. And finally, we have here our propulsion systems, which are modeled using an average load model behind its input lit LC filter. And here the auxiliary subsystems have been neglected just for the sake of simplicity. So because we use AC RMS time current curve, it is important to calculate equivalent RMS value of the DC transient current to compare it to its time current curve. This is done here using a discrete RMS algorithm with a properly selected integration window. The RMS current is then compared to the fuse time current curve, and the melting energy is calculated. If the fuse total melting energy is reached, a trip signal is sent to the fuse opening block, as mentioned earlier. What I'd also need to mention here is that I didn't plan to go into the details and the maths of all these models, but if people are interested, I'm providing reference to our work at the end of this presentation as well. So the opening phase of the fuse is modeled using a piecewise linear increasing resistance starting at time Tm when it receives, in fact, the trip or melting signal coming from the detection block. So it's pretty simple here. Regarding the HSCB detection and opening model, like I said earlier, the high-speed circuit breaker is modeled in two blocks. We have the detection block, which is the HSCB trip coil, and we have the HSCB arc function defined by HSCB manufacturers. And one important thing that I mentioned earlier is that the detection time and the mechanical opening delay of the circuit breakers depends on the waveform of the transient fault current, and they need to be considered somewhere in the model, and this is what the HSCB trip coil model is taking. This is where it is taken into account. So here, as it can be seen on the figure on the left, we see that the detection time of the high-speed circuit breaker decrease with the prospective current for an equivalent first order model, and we see that it increases with the time constant of the circuit. And on the right, what we see is that according to HSCB manufacturers, an opening delay, Tm, is required before the breaker contacts start to open. And this delay depends on the initial rate of rise of the current, which is here di over dt. In fact, as we can see here, as the initial rate of rise increase, we can see that the mechanical delay will decrease. So here's what I want to show you is a list of the different models that have been implemented in EMTP, and those that are in blue are those that I'm going to present you in more details in this webinar. First, we have power source, we have auxiliary converter, NiCad battery, we have cables, we have overcurrent protective devices, circuit breaker and fuse, and we have a complete load models, which is here, can be composed of transient voltage suppressor, MOV, reverse blocking diode, and rush limiting circuit loads model. We can have resistive load, constant power load, and constant current load. So regarding the auxiliary converter, which is the LVPS, look for low voltage power supply, it is modeled using an equivalent circuit. It is modeled by a voltage source behind a nonlinear resistance and a output filter. And this voltage source here, Vmax, and this resistance, this nonlinear resistance, RVI, is used to replicate the VI characteristic of the converter behind its input filter. Typically, the VI characteristic is composed of 3 segments. We have the droop control zone, we have the overload protection zone, and we have the short circuit protection zone. Regarding the NiCad battery models, there is a lot of details in it. First of all, there is a lot of characteristics that this model is considering. First, we have the polarization resistance, which is the variation of the internal battery voltage as a function of the battery current. We also have it's also taking into account the polarization voltage, which is the variation of the internal battery voltage as a function of the battery state of charge, SOC. It also takes into account the hysteresis effect between the charge and the discharge of the battery. It takes into account the Berger effect, which is the decrease of the battery available capacity as a function of its discharging current. And the model also takes into account for temperature effect, which is here the decrease of the available capacity as a function of the temperature. And finally, it takes into account for the variable internal resistance, which is here a function of the default discharge of the battery. So we'll look at these at the 4 characteristics that are here in blue. First of all, the hysteresis effect between the charge and discharge. What we can see here is that the hysteresis effect is in fact a chemical phenomenon that leads to the creation of 2 different paths, depending on whether the battery is charging or discharging. So we see here that in blue we have the path when the battery is discharging, and we have the path here in red when the battery is charging. And this is due to chemical losses in the battery. Regarding the Berger effect, in fact, Berger's theory states that the available capacity of a battery decreases as the current discharge rate increases. Manufacturers specify the total battery capacity at a given discharge rate, here called IN for the nominal current. Typically, the nominal capacity of NiCad battery in the rail industry is given for a discharge rate of 0.2 IN, or also called C5, which we can see here. For example, here, if we consider a battery with a Berger coefficient of 1.1, which is here the curve in green, what we see is that if we discharge the battery at 2 times its nominal current, its available capacity drops to 80% of its nominal capacity at 0.2 IN, which is here. Another effect is the temperature effect on the battery available capacity, and what we can see here on this figure is that for very cold temperature we have a loss of available capacity, and for very high temperature as well. And finally, the variable internal resistance is also a function of the depth of discharge, and it is what we can see here. We can see that as the depth of discharge of the battery is increasing, we see that the internal resistance of the battery is also increasing. And what is interesting here is that we see that between a depth of discharge of 20% and 80%, we see that the internal battery resistance can double. And all these parameters are taken into account in the EMTP models. So the battery model has been validated by manufacturers, and it shows here that we have a pretty good fit for a depth of discharge of 0% to 80%. And it's pretty good because we never intend to use our battery beyond a depth of discharge of 80%. The battery model also been validated using emergency scenario tests. And what we see here is that for an equivalent discharging current that has been done during the test, we can see that the EMTP model pretty fit the reality, and we see that the voltage error is pretty low, and the average error, I can say, is 0.5%. And the model has also been validated during short circuit tests, and we see here that we have a pretty good fit. And I saw from field testing that we have a good fit for fault current up to 30 seconds of duration. regarding the circuit breaker models, typically what we use is molded case circuit breaker type. The model, again, it's like the other protective devices model. It is modeled in two blocks. We have the thermomagnetic trip block, which is used to replicate the thermomagnetic trip curves of the circuit breaker. And we have the opening block, which is there to recreate the arc of the circuit breaker once it tripped. And the arc model that is used here is what we call the Schwartz Art Model. Regarding the load model, the components of typical loads that we can see here on this figure, we can see that we can have fusing elements, overvoltage protective device like MOV, TVS. We can have reverse blocking diode, on-off voltage control circuit that are there here to protect the equipment. Again, transient any kind of transient, mainly transient over voltage. We have an inrush limiting circuit that is there to limit the current, the inrush current of the input filter capacitor. We also have a hold-up circuit here that can sustain the voltage to the load when the voltage at the input decreases. And how it is modeled in EMTP, it is modeled in two blocks again. We have a equivalent load model that is here to represent the load behavior and its on-off voltage control circuit, and all the load front end that are here, the hold-up circuit, input filter, and rush limiting circuit, and all these devices in front there can be taken into account in the load front end model. And here, the equivalent load model, it is there to model the behavior of the load. For example, constant power load and constant current load. So constant power load, what we see here is that as the voltage increases, the current will decrease. And it is modeled using a current source that is controlled to replicate this equation here. And for constant current load, it's a constant current source, but it is controlled using an on-off voltage control circuit. And why we are doing that is because these loads typically have internal voltage power supplies. So when the voltage drops below a certain value, these loads won't be able to work. So we are modeling it in EMTP. So now here's some example of case study. First of all, if we are doing what we see here, if we are doing a short circuit here at the output of this high-speed circuit breaker, the fault current that's going to be seen by the vehicles will depend on the location of the train throughout the DC traction power systems. So what we can see here, let's neglect substation B here. If we are close to substation A, we are expecting to have a high rate of rise on the current and also a high peak current. But as we are moving away from the substation, we see that the rate of rise will decrease, as well as the maximum steady state current. And this is why we want to model in detail the substation and the train and the track, so we are able to simulate these different cases. So we can do different studies with this model. For example, we can compare a fault that is outside the propulsion system against a fault that is inside the propulsion system. First, what we can see here is that for a fault, what we are doing here is we are comparing the HSCB performance. So we're doing fault here and fault there, and we are looking at the high-speed circuit breaker performance that is here to break the fault current. So what we see is that for a fault outside, we're going to have a high peak let-through current, but the fault will be interrupted quicker than for a fault that is located inside the propulsion systems. And the main reason is that this fault here is located downstream of the propulsion system input filter, so the current, the rate of rise of the current is very slower than for the case where the fault is outside. For this case here, what we see, we are again studying the high-speed circuit breaker performance, which is here, and we are studying its performance for a different case depending on where the train is throughout the DC power traction, DC traction system. So what we are doing here, we are varying the distance here between each of the substation, and we are looking at the fault current and the high-speed circuit breaker performance. So we see that depending on where the train is, we can have very different available fault current, as I said earlier. So we see here in dashed line different available fault current. But the current that will really flow into the circuit due to the circuit breaker arcing action will be the current that is here in full line. And what we see is that we have very different performance of the high-speed circuit breaker depending on where the train is. And finally, again, let's put if we're doing a fault here, we can study we can do selectivity analysis between the high-speed circuit breaker and these collector shoe fuses. What we see here in black is that if the high-speed circuit breaker is there to interrupt the fault current, we're expecting to have a low peak current, and the fault current will be interrupted really fast. However, if the high-speed circuit breaker fails to open, we can study using EMTP that depending on the number of fuses that are available at the time of the fault, we can see that the maximum current will increase, and it also we can also see that the maximum clearing time will also increase as well. So for the second case, it's a overcurrent protection example. So what we see here, we have a DC auxiliary power system, which is what we see. We have a auxiliary converter in each of the B car. We have battery in each of these B cars as well. And we see that we have circuit breaker there that are there to isolate the vehicles when there is a fault. So we are doing here a fault here in F1. What we are expecting is to have fault current contribution from this battery here, from this converter there, and from the converter in the B2 car and the battery in the B2 car as well. So we are expecting, since this circuit breaker is closer to the fault, we're expecting this circuit breaker to open first and this guy here to open second. And once these two circuit breakers will be completely open, what we're expecting is to have the C3 car completely isolated. So here is the EMTP simulation results. We see that we can have a lot of detail. We can look at pretty much at a lot of signals. What we can see here is that when the fault is applied, we have a high fault current here, but the current rapidly decreased to 2000 amps. And the main reason is that we see here is that the B4 circuit breaker will open in its magnetic region, so it interrupts the fault current really quickly. However, since the B2 circuit breaker is further from the fault, we see that the fault current falls into its thermal region, and it's what here we can see is when it reaches 1, it means that the total thermal energy of the circuit breaker has been reached, so it trips here, and the fault current is now 0. Another thing that we can see in, using the model is that during the fault here, what we see there is that the low voltage decreases a lot, such that the load current will decrease because they are disconnected using the on-off voltage control circuit. When the B4 circuit breaker here trip, what we see is that the voltage in the B4 and A5 car comes back to normal, and it will do the same when the B2 circuit breaker will open. We will have our voltage back in the A1 and B2 car. And we see here that once the fault is completely interrupted, there is no voltage in the C3 car because it is completely isolated. So what we So what is important here to remember is that for overcurrent protection, we need to consider the transient behavior of all the short circuit sources, short circuit current sources in the circuit. For example, filter capacitor will have a high contribution at the instant of the fault, but the current will rapidly settle to zero because it acts as a open circuit once it is completely discharged. Also here what we have is that we need to consider detailed battery models, because when we are studying long fault duration, the decrease of the current is non-negligible, so we have to consider that. So we cannot consider batteries as a simple constant voltage source behind its constant internal resistance. And finally, what we have here, we have our converter model, the converter contribution. And what we see is that, again, because of its output filter capacitor, we have a high discharge at the beginning of the fault, but the current rapidly settled to a constant value because the converter is operating in its short circuit protection region in its VI characteristic. So what I can say is that detailed models are needed here, and EMTP can consider the behavior of all of these elements when we develop detailed models. So regarding the case number 3, which is a overvoltage protection example, what we still have the same power systems, but now I had here a MOV and a bus filter, which is mainly a big capacitor there to clamp the voltage during transient overvoltage events. What we see here, we are doing now a fault here in F4. And why we do a fault here in F4 is because this guy here, this circuit breaker BCB2 in the B4 car, will see the fault contribution of both LVPS and both batteries. So he's going to have to interrupt a high fault current. So we're expecting the circuit breaker to operate in its magnetic region because, again, there is a lot of fault current. And in this case, we're expecting to have a maximum transient overvoltage because we are having the maximum energy stored in all the inductance of the system. So what we see here is the EMTP simulation results. Let's look at the B4 car voltage because it is the closer, because the circuit breaker is here in the B4 car. So we're expecting the maximum transient overvoltage in this car. What we see is that when there is no overvoltage protective device, we're expecting the voltage in green, which is almost twice the nominal voltage of this system, which is 110 volt AC. When we had the MOV, what we see that we have a slight decrease in the transient overvoltage. However, when we had our filter capacitor, we see that the voltage is really clamped. And another thing that we can also see is that as we are moving away from the circuit breaker, the transient overvoltage, of course, decrease as well. So what it is important here to remember is that circuit parameters and switching devices arc influence are important to be considered when we're studying overvoltage. And the insulation coordination with overvoltage protective devices is highly nonlinear. And in fact, circuit parameters, arc behavior, and overvoltage protective devices nonlinear behavior can all be considered with detailed models in the MTP. So here, the last case is a battery sizing analysis according to the standard, the IEEE standard 1568, which is a typical standard in the rail industry. We are sizing the battery for an emergency scenario, which is mainly the primary power failure. So we are losing the power coming from these two LVPS because the track is now dead. What we generally have to do is to establish the load profile. So we need to determine an emergency load shedding scenario. The typical duration is around 60 minutes, and here, for the sake of simplicity in this study, the work assumption that I made is that we only have one battery that is available. So we're studying only one battery that needs to support the whole emergency scenario. What we are looking at is the load voltage and the available capacity, and we are trying to make sure that they are following the IEEE standard requirements. So again, what we can see is that we can see that we have a lot of details that we can look at. Here it's the MTP Simulation Results for a battery nominal capacity of 65 amp hours. What we see here, we have here our battery current, which is also the load profile that we have to establish. What we see here is that as the voltage, as the time increase, the voltage of the battery decrease because it is discharging. And we see on here this graph that the available capacity of the battery is also varying throughout the simulation time because of what I mentioned earlier. We have the Berger effect, and we have to take into account the temperature effect of the battery. So what we are looking at, we are trying to make sure that the load voltage will meet the IEEE standard, and that the available capacity, which is represented here by the battery state of charge, will meet the IEEE standard requirement. And what we see here, what we see here is that for the voltage we have enough margin when we compare the load voltage to the minimum voltage that is admissible at the load. You see that we have this this small voltage margin. But when we look at the state of charge, we see that here the battery state of charge cross the total SOC limit that is due to both the design factors and the available capacity variation that is there. So here the capacity limits is not met. Now, if we increase the battery nominal capacity from 65 to 85, we see now that we gain in voltage limits, in voltage margin, and now the available capacity is sufficient to support the emergency profile, because here we see that the battery SOC doesn't cross the SOC limit, which is the red dashed line here. So now the available capacity requirement is met. So to finish for this case, in battery sizing analysis, the behavior of the battery, the vehicle's voltage drop, and the behavior of the loads need all to be considered. And we can all do that with the MTP, having a detailed battery model and having detailed load model. So we see here on the pie chart on the left a typical load distribution in rail vehicles. Typically, we have a 50% constant power load. You see here it's an average based on different projects. So we have here 33% of constant current and 70% of resistive load. And what we see on the graph on the right is why it is important to consider the variation of these loads during battery sizing analysis. We see that in this example, we see that when the voltage is equal to VL1, all the resistive, the constant current, and the constant power loads are operating at the same current. But when the voltage drops from VL1 to VL2, we see that the current of the resistive load will decrease, while the current of the constant power load here will increase. And the overall increase or decrease, so the overall variation in the load current, will depend on the value of the resistive loads and constant power loads power. So now we are at our complete overcurrent protection example in MTP, but first I will just show you the reference that you can take a look at. There is a lot of details on the model, so all the maths are there if someone is interested in looking at it. So here, again, I put a schematic just to simplify my explanation here. Here we have a different DC auxiliary power systems than from the previous case study. Now we have a 37.5 nominal system, and we have LVPS in each of the B and C cars, and we have batteries in each of these cars as well. And we see that we have circuit breakers there and circuit breaker there, and we have a battery circuit breaker that is over there. We'll go into one of the vehicles. I'll go into the C3 vehicles because everything is there. So we have, like I showed in my presentation, we have our LVPS that is there. We have the NiCad battery model. We have a circuit breaker, and we have a ground fault detection devices. Here the loads are neglected during the overcurrent protection analysis. So inside the LVPS, what we can see is that we have our output filter capacitor. The inductance is neglected. We have our diodes here, and we have the block that model the VI characteristic of the circuit breaker. And we can go in there and see that it is modeled with a voltage source behind a nonlinear resistance, and all this logic there is there to take into account the fact that under short circuit condition, the converter will generally try a couple of times to recover before it falls in a complete lockout. So it is done using the control library of EMTP. So inside the NiCad battery model, what we have here, we see that there is a lot of control block. I won't go into the details of that, but we can see that there is a lot of details to take into account all these parameters in the model. And here, inside the circuit breaker, we have our HART model, which is here, and it receives a trip signal coming from here, which is the detection block that recreates the thermomagnetic trip unit of the circuit breaker. And what we can see is that both, when we have a two-pole circuit breaker, we need to model these two poles using two voltage source that recreates the HART voltage function. So I won't run the case. I already run the case, but you can see here that the simulation time step is 5 microseconds, and the total simulation time was 1 second. And we can see that the total simulation time was 36 seconds, which is pretty fast because there is a lot of details. We are modeling all the details of the battery. The temperature is updating automatically and during the fault. And also we are modeling the arc at the opening of the circuit breaker, which needs a lot of details. So here, what we are going to look at is the fault current. So we see, we can see at the fault current, we see here these two parts there. It's the contribution of the converter that tried to start again. But the converter fall in lockouts here. Another thing that we can look at is the battery current. Here what we can see is that the C3 battery the C3 battery fault current will be interrupted first. Then we interrupt the fault current in the B4 car, and finally we interrupt the current in the B2 car. What we're going to look here is to the travel energy, what we call the thermal and magnetic energy of the circuit breaker. We are looking at the circuit breaker in the B4 car. What we see here is that the circuit breaker will interrupt the fault current in the B4 car in its magnetic region. And we see that we send a trip signal that I will blink here. We send a trip signal at time 36.38 millisecond. We're sending a trip signal to the circuit breaker arcing function. So now, if we are looking at the transient overvoltage, at the voltage at the loads, if we go at 86.38 millisecond, we will see that the arc of the circuit breaker is modeled, and it is what we see here. And if we consider that the circuit breaker here is a ideal switch, and we do not consider the arc voltage function, it will lead to unrealistic transient overvoltage, and it will also lead to oversizing the overvoltage protective devices as well. So I think it's the end of my presentation. So I will give the power back to Henry, which will conclude my webinar.
Okay, thank you very much, Maxime. It was a very amazing presentation. I'm using EMTP every day, and I was really impressed with the level of detail you get into, and especially by the fact that you are running simulation at last 60 minutes. It's huge. But I mean, nowadays transient software like EMTP are faster and faster, and slowly we have this possibility to run very long simulation. It opens a lot of doors to precisely design equipment like battery, for example. So thank you very much for presenting that. It was very interesting, and I'm sure the crowd today really enjoyed it. So for the future webinars, in May 11th and 12th, we will do another webinar on the new protective relays library. So we will present, it will be a general presentation on all the relay that will be available on this library. So it will be very interesting. Another very interesting event, especially for the American continent, we will have our user group the 21st of July. So it will be in Boston right after the IEEE PES general meeting. So don't hesitate to have a look at our website if you want to register. We are also looking at speakers. So please contact us if you are interested by this event. Okay, so thank you very much. Here you can find the contact information in case you would like to try EMTP or get a quotation. Again, don't hesitate, contact us if needed. Also, please take some time when you leave the webinar to fill our small survey. We ask you some technical questions on how you study railways application and what tool do you use and what features are you missing, so we can orientate the development of EMTP so that we reach your needs. So again, thank you very much for attending this very good presentation. Thank you very much, Maxime, for doing it. And I will talk to you very soon. Bye-bye.